Anybody been duped by Simpson's paradox before? Or, yeah, it hurts. Definitely hurts. So we're going to talk a bit about some statistical tests and algorithms that we produce to find occurrences of Simpson's paradox in data. So I'm just going to talk a bit about what Simpson's paradox is and the algorithms that we use to detect Simpson's paradox. And then Nazanin is going to give a live demo of some GitHub code that we have for looking for cases of Simpson's paradox in data. Okay, so can you trust the trend? Do you want to be duped by your data? So, okay, so I'm a Stack Exchange question answerer. And so I log on to Stack Exchange at 8 p.m. and I start answering some questions one at a time. So do my questions get better as I answer them, or do they get worse, or do they stay about the same? And here, when I say better, I mean the probability that they'll be accepted as the best answer. So who thinks my questions get better over time as I answer more questions? Okay, some people. Who thinks they get worse? Then maybe I get fatigued. Worse? Okay, yeah, okay. So on average, questions get better. So here on the x-axis, we have answer position within a session. And here on the y-axis, we have acceptance probability. So actually, the trend is increasing. So basically, as you go on throughout your session, your answers get better. Okay, another example. So look at Reddit. So as people spend more time on Reddit, so let's just say they sign up, and then they're on Reddit for a year, 2 years. Do Reddit users get more active over time or less active? Who thinks they get more active over time? Okay, one. Who thinks they get less active? Okay, more people. Okay, they get more. On average, Reddit users get more active over time. So the question is, can we trust these trends, these univariate trends? And the aim of our algorithm really is to see if these trends are true, or if there's some confounding factors that basically cause the trends to appear as they are. I mean, and I guess as data scientists, we all know that we see a result and we say, oh, we can explain this by, or okay, this is counterintuitive, but here's an explanation. We can kind of explain anything. So I guess getting to the roots of the Simpson's paradox is a kind of a better way of finding true patterns within the data. So what is Simpson's paradox? So Simpson's paradox is basically a trend, when a trend appears different in subgroups, and then it disappears or reverses when we aggregate. So here, if we look at the Simpsons family as each subgroup, so we can see that we have some downward trend, but then when we aggregate over every member of the subgroups, every member of the family, that the trend is actually increasing. So at the lower level, we have some relationship which is decreasing, but just purely by aggregating, this trend reverses. So that this aggregate trend is obviously something that can be misleading and lead to misconclusions, and as such is quite dangerous for data analysis. So an illustration, so do smokers live longer? So here was a study, it was actually from a stats blog. Looking at mortality rates for smokers versus non-smokers. So actually, smokers have lower mortality rates than non-smokers, which I guess is a surprising conclusion. But let's look at each age group. So here's different age group for smokers. And we can see that within each age group, smokers, which is the blue line, actually has higher mortality rates, even though on the aggregate they have lower mortality rates. So what's going on here? And basically, it's an effect caused by the way the data is distributed within the subgroups. So here, let's look at how the percentage of populations for smokers on the left versus non-smokers for each age bracket. So we can see that here, for the smokers, only 8% are over the age of 65, whereas 27% for the non-smokers are over the age of 65. And I guess mortality rates are generally higher for people who, for older people. So the higher weighting towards older age groups causes the data on the aggregate to become larger, the mortality rates. So for example, when we're calculating the mortality rate for a non-smoker, we multiply the mortality rate for this age group, which is quite high, 75, by 9%, and this other high one by 18%, whereas for the smokers, we're only multiplying the high by 2% and the second highest one by 6%. So the trend is clearly reversed. So even though smokers at the individual level have higher mortality rates, when we aggregate them, the reverse trend is shown. So here's an example from Tala, where I work currently, which is, so Tala gives credit based on alternative data points, so non-financial data points. So we use people's behavioral data from their mobile devices to predict repayment and to kind of create credit scores. And one of our competitors, Branch, found a kind of counterintuitive result that actually people who gamble more have higher repayment rates. So I guess you could think that's maybe a bit counterintuitive. People who spend more money gambling actually repay loans at a better rate. And indeed, actually looking at our data, we got the same result. So on the x-axis here, we have the gambling spend, and on the y-axis, we have repayment rates. So people who gamble more repay our loans actually at a higher rate. But there's a confounding factor here, which is time. So generally, people with older devices or who have more data, or data going back further, actually have higher repayment rates. And the more data they have, the more information we have on gambling habits. So that actually, when we look at gambling spend per day, the trend reverses. Actually, people who gamble more per day have lower repayment rates. So another occurrence of Simpson's paradox within our data. Okay, so all very interesting. And now I'd like to talk just about the method and the algorithm that we use to detect Simpson's paradox within data. So we developed algorithms to systematically identify Simpson's paradox. So basically, we give in a matrix with some response variable and lots of predictor variables, and then our algorithm returns pairs of Simpson's paradox pairs, i.e. there's a trend with one feature that reverses when we condition on another feature. So for example, a trend on gambling that reverses when we condition on time. So how does it work? So for each covariate, for example, I talked earlier about stack exchange and answer position. We basically estimate the trend in the outcome variable, which is acceptance probability, with respect to the variable. In this example here, we just use a linear model, a logistic regression model, to fit the trend. And we get some coefficient, linear coefficient, which we can see, is it statistically significantly increasing? Is it 0 or is it decreasing? Then we look at the other covariates and we disaggregate the data. So here, for example, we're looking at session length for answer position. So actually, how many answers did somebody perform within a single session? So earlier we looked at answer position, and now we're saying actually how many answers were there. So here you can see in the table, the majority of people who use stack exchange just answer one question. Some answer 2 questions, and it kind of tails off pretty quickly. And then for each of these subgroups, we fit other linear models. So for example, for people with session length 1, then there can only be one answer position because they only answered one question. For people with session length 2, there's 2, their first question and their second question. For people who answered 3 questions, session length 3, there's 3 data points. So the first answer, second answer, third answer. And we see here that the trend reverses. So actually, your intuition was correct, that actually as you answer more questions, the acceptance probably decreases, so your answers somehow become worse. But when aggregated over all of the subgroups, we get the other trend. So basically, to conclude just about the method, so we fit a model to the covariate, and then we disaggregate the covariate, or sorry, the confounding feature, and within each subgroup, we fit linear models. And then we compare the trends, we compare the slopes to see if there's reverse behavior. Okay, so disaggregation, that's cool for the number of sessions because it's got low cardinality. There's very few actual number of session lengths. But what about some more continuous high cardinality features? For example, the number of answers that somebody's ever answered on Stack Exchange, which goes from 1 to 10,000. So we can't look at each number, fit a regression model there because we have very few data points per subgroups. So I guess the question is, how do we disaggregate if we have continuous variables? And the solution for us was to basically fit a tree. So, so here we look at answer position again and acceptance probability, and we see this trend. And here then is the feature number of answers, which I said can take a very large range of values. So what we do basically is we fit just a decision tree of acceptance probability versus number of answers, and that allows us to bin the variable into maybe like 10 different bins. So you can see here that the lines on the y-axis are the different bins. So there's one from one answer to maybe 100, another from 100 to 500, and so on, which is basically got from a decision tree. And then within each bin, we fit a logistic regression model, and we get these reversal of trends. So that's how we kind of disaggregate for continuous data. Seems to work pretty well for us. Yeah, so basically we disaggregate, compare the trends, compare them to the original trend, and if we find opposing behavior, then we've found cases of Simpson's paradox and a case to say that, okay, maybe you've observed a trend, but actually it's just a result of the way the data is aggregated, and actually the trend is different at the more microscopic level versus on the fully aggregated level. So we've applied this method to some data sets, including I told you about Stack Overflow, also some interesting ones on Khan Academy and Duolingo. I won't talk too much about them, but they're in our paper if you want to check that out. So yeah, I just want to highlight one of our results was previously found just in a different paper that our result kind of picked up, and just found through traditional data analysis and kind of, just deep data diving into the data. So I think this is kind of a tool that not only let us like avoid Simpson's paradox, but by actually finding Simpson's paradox, we find these interesting patterns in our data set and interesting kind of correlations between features. So I think it's a really useful tool for both, avoiding misconclusions and also finding like interesting data with interesting patterns within the data. So to come back to the earlier question, yes, answering performance decreases as you answer more questions. And also for the Reddit one, that actually users become less active over time. So here the confounding variable is basically, it's a survival bias. So here we're aggregating overall users, and here these individual lines are, the green one is user who've been on a platform for 0 to 1 year. This is from 1 to 2 years, and you can see that within these subgroups, actually user behavior actually decreases. They become less interested over time. Okay, so now I'm going to pass on to Nazanin, who's going to give a demonstration.
I'm going to go through a little example on our GitHub. Our GitHub is available public, you can use it. For the composition part, we are using C++ because it's pretty fast. But for trend reversal part, we are using Python since it has good packages for trend analysis and plotting parts. We have used bash script for connecting these two components. And the output of the algorithm is a series of PDF files. For each pair, we have a PDF file with 4 plots, which helps you to understand what's going on in that Simpson's paradox pair. The only thing you need to do for using the code is working with these 2 files. Run.sh, you basically don't need to do anything with that. You just need to run it. But for input.json, you just need to specify hyperparameters for the algorithm. The first parameter is your dataset name. The second one is target variable column, which is 0-based. Target variable name, which is going to use for using in plots. The other one is number of beans, which is going to use on binning part for, this is maximum number of beans for each of those conditioning variables. And least number of data points in each bin is the minimum number of data points in each bin. These two green ones are stopping criteria for the binning algorithm, which is using R-squared measures, which is maximizes R-squared measures for the bins. The other two parameters are level of significance, which is going to use for deviance. We are checking if whether or not our trend is significant, and after that we are going to see the trend reversal is significant or not. The log scales is using for the plots. If you have a heavy-tailed variable, you can set the log scale as true for that particular variable, so the plots looks better for that variable. The output files are five type of output. It's beans.csv that tells you that what are the beans for each of those variables. Entry is number of data points in each of the beans. It's correspond to beans.csv. And y bar tree is average value of y for each beans. Or code is for binary variables. So y bar tree is a value between 0 and 1. R-squared improvement is R-squared improvement for each of those variables. And for each of those Simpson's paradox pairs, we have a PDF file. For example, as you can see in second exchange data, we have 7 different Simpson's paradox pairs. So we have 7 different PDF files for each of those pairs and 4 plots for each of those pairs. Now I'm going to show you a demo. This is our GitHub repository. I'm going to clone it. This is the repository. We have a sample input here, which is a part of Khan Academy dataset. But for demo purposes, I've generated, it takes time, so I don't want to bother you. I've generated a small example, synthetic example, which only has 2 variables and 1 outcome, binary outcome variable. And the plot looks like this. This is x1, this is x1, and this is y. Y increases as a function of x1, but if you condition on x2, which are these colors, y decreases in terms of xy. So let's run our code on this data, copy, and I'll paste it as in input file. The only thing you need to do after pasting the data here is to change this input info.json file. I want maximum number of bins to be 10, and least number of data points to be 1. The name of target variable is y. Target variable column, as you see, is 2 because it's 0 base. I leave level of significance as 5%. The CSV file name is downward binary. I don't want to ignore any column, and I don't want to use log scales. I think it's ready. Now I'm going here. I just need to run this, run.sh. Finished. As you can see, we have lots of information in our log. The target variable is y, features are x1 and x2. We have our squared improvements here, and once it have found a trend reversal, it searches for significance of a trend reversal, which is here it's significant, and it's going to write output in our output file. We have 1 pair and 1 PDF. As you can see, the trend is upward. y increases by as function of x1, but when you conditioned on x2 here, we have reverse trend. And the other two plots are these two. This is a histogram, two-dimensional histogram of x1 and x2. The color is y here. And as you can see, in the aggregated version, it starts from blue and goes to red, but at this disaggregated version, it starts from red and goes to blue. It becomes bluer. And the other outputs are here in temporary files. We have beans.csv. Maybe it's better to show you the real data. Here, this is part of Orhan Academy data. For example, here for all problems, the first bean starts from 5 and goes to 20. The second bean starts from 20 and goes to 47, and etc. This is beans for all of the variables. And this one is number of data points in each of those beans. 2,000 data points, 900 data points in each of those beans. This is corresponded to beans.csv. And in this one, we have average y value for each of those beans. And R-squared improvement is this one, which this is R-squared improvement for each of those variables. For example, session nums, session index, or all of them. Back to slides. To summarize, Simpson's paradox exists even in your data, so you must care about it. And you can use our algorithm to find Simpson's paradox in your data if you have binary outcome variables. And our future work is to find a more robust statistical version of finding this trend reversal. Currently, we report a pair as a Simpson pair when more than half of the subgroups have opposite sign with the aggregated data. But we believe that there are more robust statistical versions for this, and we are already working on that. And thank you. If you have any questions, we will be happy to answer. Yes.
Can you also look at subgroups to determine the trends? Do you need to look at subgroups to determine if there's outliers in your data?
Can we get a mic over here, actually? Yeah, I think, so the question was if you need to look at subgroups to determine trends, then do you need to look at subgroups to determine outliers? That was a question. Yep, good question, sorry. Yeah. So I think when dealing with human behavioral data, distributions of features and variables are often very heavy-tailed, which is to say that lots of people, for example, if you look at a social network, and you look at the distribution of connectivity, lots of people have maybe 100 connections, 200, 1,000 connections, but there are some people with 1 million connections, and they are, I guess, the outliers. Or, I mean, it's whether you call them outliers or whether they're just, you know, it's a tricky question of whether it's an outlier or just it's a fact that the distribution is heavy-tailed like that. Oftentimes you can imagine then that outliers have drastically different behavior than the typical members of the population. So I think that by decomposing into subgroups like that, you can maybe understand why your outliers exist versus just maybe thinking that it's some, you know, y value that has deviated a lot. That maybe it does occur because, you know, the underlying data has distributions that are very heavy-tailed, and because of them heavy tails that there are this 0.001% that have these very, very high data points, and that is what could explain the outliers in your maybe outcome variable. So I think, yeah, that breaking down underlying distributions into subgroups, especially when dealing with heavy tail data, is always a good approach.
Is there a way do you think, to generalize this approach from subgroups, along one covariate, or one confounder to like multivariate clusters of subgroups that might have to deal with interactions between different variables?
Yeah. So maybe you're saying like multiple confounding variables. Is that it?
Yeah, like the subgroups could be clusters that are determined by in a
Yep.
higher dimensional space.
Yeah, sure, exactly. So at the moment, our confounding variables are basically, we just like condition on one variable. I guess our clusters as such are just these like bins or these like subgroups of that confounding variable. But yeah, I guess one of the immediate ways we thought about generalizing it was to try to, I guess, condition on multiple covariates or multiple variables, and I guess kind of bin them so that you have these kind of clusters. I think for us, more pressing was just maybe getting our statistical tests down better before actually generalizing it to multiple dimensions. And but yeah, I think definitely there could be more interaction terms there that could be captured. Definitely, yeah. I mean, our methodology is definitely by no means perfect, but certainly we have found it useful for finding maybe more obvious ones, or ones where a kind of a clearer trend exists on that kind of two-dimensional interaction.
So it seemed like the sample size across each subgroup sometimes varied considerably.
Yep.
If you normalized or tried to subsample so that you had equal number of samples across the subgroups, does that affect the results?
Big time, yeah, definitely. So essentially, you can't get Simpson's paradox if your subgroups are the same size. Yeah, so it's basically an artifact of your subgroups being, it's essentially, that's the root cause of Simpson's paradox is kind of that your subgroups are of different size, but also that there's some variation of the relationship of the outcome variable within these subgroups. So if your subgroups are of differing size, but your response variable is the same across them, then you won't have a paradox. If your subgroups are different, and the other way around too, so you need differences in subgroup population, and then also the response variable stuff, exactly. So yeah, so in terms of experimental design, if you know there's going to be some, for example, the smoking one, if you just fix the distributions within each age groups, then you wouldn't have had the paradox. It's purely a result exactly of difference in distributions. Perfect.
Have you considered any sort of unsupervised methods for your clustering? So like if you just take out the target variable and then use k-means to create the clusters in a multivariate fashion. Yep. Have you tried that in any way?
Nope, haven't tried it, but definitely we're open to new ways of doing it. So if you want to do a pull request, submit some clustering technique, or even I'd be happy to talk more about it afterwards. I guess in general, Simpson's paradox relates to some kind of response variable, so that when it came to binning, I guess the first thing we thought of was kind of fit a tree and just get the more homogeneous subgroups by their relationship with the outcome variable, which worked pretty well. If you do even binning, it doesn't work well for these kind of heterogeneous distributions, which if you can picture, you need to plot the histogram on a log scale, and even binning doesn't capture it well. If you do log scale binning, that's not the perfect solution, or percentile binning either. So the decision tree approach worked really well. And right now we have it that you kind of specify maybe the minimum or the maximum number of bins and the minimum number of data points, but we're going to extend that so there's some kind of like cross-validation where it picks the best bins just from like a cross-validation approach. But yeah, we're definitely open to, if anybody has any ideas about statistical testing or unsupervised binning, just definitely reach out, and happy to find ways to improve the algorithm and hopefully someday you guys can try it out and might be useful.
Hi, I'm just being curious that do you guys have any collaboration with ISI?
Yeah, so Nazanin, do you want to take this one?
Yeah, I'm PhD student at ISI.
Yeah.
And my supervisor, my advisor is Christina Lerman. Yeah, that's it.
Yeah, and before Tala, I also worked at ISI. I was sponsored by the James S. MacDonald Foundation on a fellowship there, so this was work that we did together in ISI. Yeah. Okay. Perfect. Thanks very much.